On a clear autumn night, far from city lights, there is a faint smudge of light, visible in the constellation that ancient astronomers named Andromeda after a princess from Greek mythology. The smudge appears soft and fuzzy, nothing like the sharp points of stars surrounding it, and finding it requires patience and dark-adapted eyes willing to search the heavens carefully. I remember the first time I found it, that gentle blur among the sharper stars, and the strange feeling that came with knowing what that blur actually contained within its distant glow. That faint patch of light holds the key to everything our night sky will become across the next several billion years of cosmic time. The smudge is a galaxy, an entire island of stars, separate from our own Milky Way, containing roughly 1 trillion suns, all blended together by distance into that soft, barely visible glow. 1 trillion is a difficult number to grasp. More stars than grains of sand you could hold in your hands. More suns than seconds in 30,000 years of time passing. Each of those trillion stars has its own story, its own planets perhaps, its own place in a spiral structure so vast that light takes over 200,000 years to cross from one edge to the other. All of that immensity compressed by distance into a smudge that fits within the width of the full moon several times over. You are listening to The Drowsy Astronaut, and tonight we are taking a slow, unhurried journey through 4 billion years of cosmic transformation, exploring what our night sky will look like as this distant galaxy draws ever closer. There is no rush to this journey, no urgency in these timescales that stretch beyond anything humans can truly feel in their bones or their daily rhythms. If you enjoy falling asleep to real science explained calmly and warmly, consider liking this video or subscribing to join future journeys through the cosmos we share. Feel free to share in the comments where you are listening from tonight, what corner of Earth you occupy as we explore these future skies together. The light arriving from Andromeda tonight left that galaxy approximately 2.5 million years ago, traveling through the emptiness between galaxies, while our ancestors were just beginning to walk upright on the African plains. When those photons began their journey, no human had yet made a tool, told a story, or looked up at the night sky, wondering what those points of light might mean. The light traveled through void, through darkness, through 2.5 million years of cosmic emptiness, to arrive at this particular moment on this particular night when eyes might receive it. Every time someone looks at Andromeda, they are seeing ancient light, completing a journey that began before humanity existed in any recognizable form. Finding Andromeda in the night sky requires knowing where to look, and autumn evenings in the northern hemisphere offer the best viewing conditions as the constellation rises high overhead. The galaxy appears in a region of sky away from the bright band of our own Milky Way, giving it a darker background against which its faint glow becomes more visible with careful observation. Even binoculars transform the smudge into something more clearly defined, an elongated oval of soft light with a brighter center where billions of stars concentrate. Telescopes reveal more structure still, hints of the spiral arms that wrap around the galaxy's core, though from Earth we see the disk tilted at an angle rather than face-on. Ancient observers noticed this patch of light centuries before anyone understood what galaxies were, or that our own Milky Way was one of many island universes scattered through space. Persian astronomers described it over 1,000 years ago, calling it a small cloud, and it appeared in star catalogues long before telescopes existed to reveal its true nature. The fuzzy appearance led early telescope users to call it a nebula, a cloud of gas within our own galaxy. And this misunderstanding persisted for centuries as astronomers debated its distance. Only in the 20th century did careful measurements prove that Andromeda lay far beyond our galaxy's edge, a separate collection of stars at a distance almost impossible to comprehend. The breakthrough came when astronomers identified special stars within Andromeda, whose brightness could be used to calculate distance, revealing that this fuzzy patch lay millions of light years away rather than thousands. This discovery transformed our understanding of the universe, proving that the cosmos contained many galaxies rather than just our own, each one an island of billions of stars separated by vast gulfs of nearly empty space. Andromeda became the nearest large galaxy to our own, a neighbor in cosmic terms, though separated by a distance that would take millions of years to cross, even traveling at the speed of light itself. The smudge in the autumn sky suddenly became a sibling to our own galaxy, similar in many ways, yet distinct in its own characteristics and history. What makes Andromeda particularly special among the billions of galaxies scattered through the observable universe is its relationship to our own Milky Way across cosmic timescales. These two great spirals are not simply neighbors existing in the same cosmic region, unconnected and independent in their paths through the expanding universe around them. They are gravitationally bound to each other, caught in a mutual attraction that has been drawing them together since both galaxies formed billions of years ago in the early cosmos. The gap between them grows smaller with every passing moment, and the sky we see tonight represents just one frame in a transformation that spans billions of years. Looking at Andromeda tonight means looking at the future, though that future will not arrive on any timescale that humans naturally comprehend or experience directly through their brief individual lives. The light reaching our eyes shows the galaxy as it appeared 2.5 million years ago. But the galaxy itself has continued moving toward us during all that time. By the time we see it, Andromeda has already closed a significant portion of the remaining gap, drawing nearer while its light traveled the distance that still separated us. The universe operates on timescales that dwarf human history entirely. Yet we can understand these processes through patient observation and careful measurement. The faint smudge visible on autumn nights appears motionless, fixed among the stars like a permanent feature of the heavens that will never change across any span of time we might observe. This appearance of stillness is an illusion created by the vastness of the distances involved and the brevity of human observation compared to cosmic timescales. Andromeda moves toward us at tremendous speed. Yet that speed translates to almost imperceptible motion when viewed across distances measured in millions of light years and timescales measured in single human lifetimes. The change happens constantly, moment by moment, year by year, century by century, adding up over millions and billions of years into transformation. The galaxy contains stars of every type, from small red dwarfs that will burn for trillions of years to massive blue giants that will exhaust their fuel in mere millions of years. Gas clouds within its spiral arms collapse and form new stars continuously, just as they do within our own Milky Way's star-forming regions, scattered through our galactic disk. Dust lanes wind through the structure, dark threads visible against the brighter background of accumulated starlight, marking regions where light is absorbed rather than transmitted toward distant observers. The whole system rotates slowly, stars orbiting the central bulge over timescales of hundreds of millions of years, maintaining the spiral pattern through dynamics we understand well. At the heart of Andromeda lies a supermassive black hole, a concentration of mass roughly 100 million times greater than our Sun, compressed into a region smaller than our solar system. This black hole does not glow or emit light directly, but its presence shapes the motion of stars near the Galactic Center, and occasional material falling toward it releases energy detectable from across the intergalactic distance. Our own Milky Way contains a similar central black hole, though smaller, at roughly 4 million solar masses. And eventually, these two cosmic objects will also merge as part of the galactic collision. The black holes represent the gravitational anchors of each galaxy, the dense cores around which everything else orbits through billions of years of cosmic time. The trillion stars within Andromeda include many that host planetary systems, worlds orbiting other suns that we will likely never see individually across the vast distance separating our two galaxies. Some of those worlds may be rocky like Earth, orbiting within zones where liquid water could exist on their surfaces, and where conditions might favor the emergence of life. Whether any of those potential worlds actually harbor life remains unknown, and may remain forever beyond our ability to determine, given the distances and the limitations of observation. The possibility adds another layer of wonder to that faint smudge, the thought that other eyes might exist within it, looking back toward our galaxy. The autumn sky holds this galaxy like a gift, visible to anyone willing to find a dark location and search patiently among the stars for that soft, telltale glow. No telescope is required to see it. Only darkness and patience, and the knowledge of where to look among the patterns of stars that ancient observers connected into constellation figures. The experience of finding it connects us to those ancient observers who noticed the same smudge and wondered what it might be, not knowing they were seeing a trillion suns. Across centuries and cultures, humans have looked at this same patch of sky and asked questions that we are now able to answer with remarkable precision. The distance to Andromeda places it beyond the gravitational influence of our galaxy's individual stars, but within the gravitational reach of our galaxy as a whole. The two galaxies feel each other's pull across the void, a mutual attraction that operates on scales almost too vast to describe in everyday terms, yet follows the same laws of gravity that keep planets in orbit around stars. This gravitational connection has shaped both galaxies since their formation in the early universe, influencing their evolution and determining their eventual fate together across cosmic time. The relationship between these two spirals is ancient, patient, and ultimately transformative for both. The smudge into night sky appears peaceful and static, giving no obvious hint of the immense changes that will unfold across the next several billion years of cosmic time. Yet everything about that faint glow speaks to motion, to change, to a universe that never truly stands still, even when our brief observations cannot detect the transformation occurring. Andromeda approaches steadily, the distance shrinking, the eventual meeting drawing closer with every passing year, even as the night sky appears unchanged from one human lifetime to the next. The universe operates on timescales that humble us, yet we can understand those timescales and trace their consequences far into the future. The light from Andromeda tonight carries information about a galaxy moving through space, approaching across a gulf that seems permanent but is actually temporary when viewed on cosmic timescales. That motion shapes everything about what the night sky will become, transforming the heavens in ways that would astonish anyone familiar only with the unchanging stellar patterns we observe during our brief human lives. The faint smudge holds a future within it, a destiny shared between two galaxies that will eventually become one single structure containing the combined stars of both. Tonight, we see the beginning of that story, the distant view of something drawing ever closer with every passing moment. The galaxy we call Andromeda moves toward us through space at a speed that seems extraordinary by human standards, crossing distance at a rate that would alarm us if the distances involved were not so incomprehensibly vast. The approach speed of Andromeda toward our Milky Way measures approximately 110 kilometers every second, a velocity that translates to roughly 250,000 miles per hour in more familiar terms. At this speed, a spacecraft could travel from Earth to the Moon in less than an hour, covering that familiar distance almost unimaginably quickly by the standards of any vehicle humans have ever built. The galaxy crosses enormous distances by human standards. Yet the gulf between our two island universes remains so vast that this tremendous speed produces motion almost imperceptible across human timescales. The approach continues constantly, never pausing, never slowing, drawing the two galaxies together across billions of years of cosmic time. This motion sets Andromeda apart from almost every other galaxy in the observable universe, which appear to be moving away from us due to the expansion of space itself. When astronomers look at distant galaxies, they see light shifted toward the red end of the spectrum, a stretching caused by the space between us expanding while light travels across it. Andromeda shows the opposite effect. Its light shifted slightly toward the blue, compressed by the galaxy's approach, rather than stretched by recession through expanding space. This blue shift reveals the motion directly, light carrying information about the galaxy's velocity, encoded in the precise wavelengths that reach our instruments. The approach overcomes the expansion of space because Andromeda lies close enough for gravitational attraction to dominate over cosmic expansion at this particular distance. Space itself continues expanding everywhere, including in the region between our two galaxies. But gravity pulls the galaxies together faster than expansion pushes them apart. This gravitational influence operates at distances up to several million light-years, creating a local region where galaxies move toward each other rather than apart. Beyond this local neighborhood, expansion wins and galaxies recede from view. But within it, gravity shapes the motions and destinies of nearby structures. The gravitational attraction between the Milky Way and Andromeda began operating as soon as both galaxies formed in the early universe billions of years ago, drawing them toward each other across cosmic time. The two galaxies have never been stationary relative to each other, always moving under the influence of their mutual gravity, even when separated by millions of light years of intervening space. The current approach represents the continuation of a process that has been underway for most of cosmic history, accelerating slightly as the gap narrows and gravitational attraction intensifies. By the time the galaxies actually meet, they will have been falling toward each other for roughly as long as the universe has existed. Every year that passes brings Andromeda approximately 37 billion kilometers closer to our position within the Milky Way, a distance roughly equivalent to traveling from the Sun to Pluto and back several times over. This annual approach seems enormous when expressed in kilometers. Yet, it represents a tiny fraction of the total distance still remaining between the two galactic structures. The perspective matters greatly here, as cosmic distances dwarf even the most impressive motions when viewed proportionally rather than in absolute terms. The approach is relentless and steady, accumulating across millions of years into changes that eventually transform everything about the relationship between these two spirals. The blue shift, detected in Andromeda's light, provided the first clear evidence that this galaxy was approaching rather than receding, like most others scattered through the observable universe. Astronomers measure these shifts by examining the spectral lines of light, dark bands that appear at specific wavelengths corresponding to the absorption of light by various elements. When a light source approaches, these bands shift toward shorter wavelengths, toward the blue end of the spectrum, and the precise amount of shift reveals the velocity of the approaching object. Andromeda's blue shift corresponds to that 110 kilometers per second, a measurement confirmed through multiple observations using increasingly precise instruments. The discovery that Andromeda approaches rather than recedes came as a surprise to early 20th century astronomers who were just beginning to understand the expansion of the universe and the general recession of distant galaxies. Most galaxies showed redshift, their light stretched by expansion, and this pattern seemed universal until careful measurements of Andromeda and a few other nearby galaxies revealed exceptions. These nearby exceptions represented gravitationally bound systems where local attraction overpowered cosmic expansion, pockets of the universe where gravity dominated and drew things together. The local group, as astronomers call this neighborhood of galaxies, contains about 80 known members, with the Milky Way and Andromeda as the two dominant spirals. The gravitational relationship between our two galaxies is not a new development, but a fundamental feature of their existence since formation in the early universe. Both galaxies condensed from vast clouds of gas and dark matter in the first billion years after the universe began, forming in the same general region of space and feeling each other's gravitational influence from the very beginning. The attraction has been a constant presence throughout their history, shaping their evolution and determining that they would eventually merge rather than drift apart. This destiny was written into their relationship from the start, encoded in their masses and their proximity. Dark matter contributes significantly to the gravitational attraction between the galaxies, with invisible halos of this mysterious substance surrounding both spirals and extending far beyond their visible stars. The dark matter halos of the Milky Way and Andromeda likely already overlap, their edges interpenetrating across the space between the visible galactic structures. This overlap means the galaxies are already interacting gravitationally through their dark matter components, even while their visible stars remain separated by over 2 million light-years of space. The merger has already begun in a sense, though the most dramatic phases remain billions of years in the future. The speed of approach, while enormous by human standards, operates across such vast distances that the collision remains billions of years away from the present moment. At 110 kilometers per second, crossing 2.5 million light-years requires approximately 4.5 billion years, roughly the same span as the remaining lifetime of our Sun, before it exhausts its hydrogen fuel. The timescales align in a way that connects the galactic future to the stellar future, both transformation and ending arriving at roughly the same epoch in cosmic time. The universe operates through patient processes that unfold across spans dwarfing all of human history combined. The approach velocity actually increases slightly as the galaxies draw closer, with gravitational attraction intensifying as the gap narrows and the inverse square law of gravity becomes more favorable. This acceleration is subtle over human timescales, adding perhaps a few kilometers per second over millions of years, but it accumulates across the billions of years remaining until the galaxies actually meet. By the time of first close passage, the relative velocity will have increased noticeably, the galaxies falling toward each other under ever-strengthening gravitational attraction. The merger will not be a gentle drifting together, but a meeting at considerable speed, though still slow by the standards of such vast structures. Every photograph ever taken of Andromeda captures light from a galaxy slightly farther away than it currently lies, the information traveling for millions of years while the galaxy continues its approach through intervening space. When we see Andromeda as it appeared 2.5 million years ago, we are looking at a galaxy that was 2.5 million light-years distant at the moment that light departed. The galaxy has since closed a significant portion of that gap, approaching while its ancient light traveled toward us, meaning its current distance is somewhat less than the apparent distance suggested by light travel time. This distinction between apparent and actual position matters when discussing objects moving at significant velocities across cosmic distances. The local group, containing both major spirals, moves through space as a unit, gravitationally bound and traveling together through the larger cosmic structure surrounding our region. While Andromeda approaches us within the local group, the entire group moves through space at its own velocity relative to the cosmic microwave background and relative to other galaxy groups and clusters nearby. The motion within the group and the motion of the group itself combine into a complex picture of cosmic dynamics, galaxies moving within moving groups within an expanding universe. The Andromeda approach represents internal dynamics within a bound system, not motion relative to the universe as a whole. The two galaxies will not simply collide once and merge instantly, but will undergo multiple close passages over the course of roughly 2 billion years following their first encounter. Each passage dissipates some of the orbital energy through gravitational interactions, drawing the galaxies closer together for subsequent encounters until they finally merge completely. The process resembles two objects falling into an increasingly tight spiral around each other, each orbit bringing them closer until separation becomes impossible. This gradual merger spreads the transformation across billions of years, rather than concentrating it into a single dramatic moment. The inevitability of the collision removes any question of whether it will happen, leaving only questions about exactly when and exactly how the process will unfold in detail across future cosmic time. No force will deflect Andromeda from its approach. No event will alter the gravitational relationship that draws these two spirals together, across the void separating them. The collision is as certain as any prediction astronomy can make about the distant future. A merger written into the physics of the situation from the moment both galaxies began falling toward each other. The night sky will transform because the underlying cosmic dynamics make transformation inevitable across sufficient time. The gulf between our two galaxies, while shrinking, remains enormous and will take billions of years more to cross completely, despite the considerable speed of approach. The distance separating our Milky Way from Andromeda stretches approximately 2.5 million light-years across the void between the two galaxies, a gulf so vast that light itself requires millions of years to cross it. A light-year represents the distance light travels in 1 year, roughly 9.5 trillion kilometers, making the full distance something like 24 quintillion kilometers when expressed in more familiar units. These numbers lose meaning quickly because human experience provides no reference point for comprehending such immense spans of emptiness between cosmic structures. The void exists on scales that require patient explanation and creative comparison to bring any sense of proportion to the mind. If our entire solar system, from the Sun to the orbit of Neptune, were shrunk to the size of a small coin, the distance to Andromeda on that scale would stretch across a medium-sized country. The compression required to make the comparison workable reveals just how much emptiness separates structures in the universe, how much nothing lies between the somethings we notice and name. Stars and galaxies appear prominent in photographs and descriptions, but the dominant feature of the universe is actually the vast emptiness between them, the space where almost nothing exists at all. The void between the Milky Way and Andromeda exemplifies this emptiness on the grandest of scales. The space between galaxies contains what astronomers call the Intergalactic Medium, a thin scattering of atoms so sparse that each cubic meter might contain only a single particle, or even fewer. By comparison, the air we breathe contains roughly 25 quintillion molecules in every cubic centimeter, a density so much greater that the intergalactic medium seems almost like pure vacuum. This thin material consists mostly of hydrogen, the simplest and most common element in the universe, existing as individual atoms or ions, drifting through the darkness between galactic structures. The medium carries almost no mass compared to the galaxies themselves, a faint whisper of matter in the enormous volumes of otherwise empty space. Crossing this gulf at the approach speed of 110 kilometers per second requires approximately 4.5 billion years, a timescale that spans roughly a third of the universe's entire age. Since the cosmic beginning, the journey has been underway since both galaxies formed, the gap narrowing with every passing moment, while the remaining distance still dwarfs comprehension. At human scales, this approach seems frozen, motionless, the two galaxies hanging in space with no apparent change from year to year or century to century. Only across millions and billions of years does the motion become visible, the gap narrowing, the destiny approaching. Light traveling this distance carries with it the passage of time, arriving at Earth millions of years after departing from Andromeda and showing the galaxy as it appeared in the distant past, rather than as it exists now. The 2.5 million years of light travel time means we see Andromeda as it was when early human ancestors were just beginning their evolutionary divergence from other primates on the African continent, the light left during an epoch before human civilization, before written language, before any of the cultural developments that distinguish our species from other animals. By the time we receive that light, millions of years of history have unfolded on both sides of the journey. The emptiness between galaxies is not entirely empty, with occasional dwarf galaxies scattered through the void like small islands between larger continents of stars. These dwarf galaxies contain millions or sometimes billions of stars, large by human standards, but tiny compared to the grand spirals they orbit or neighbor. The local group contains roughly 80 such galaxies, most of them much smaller than either the Milky Way or Andromeda, bound gravitationally to the larger structures. Some of these dwarfs orbit one spiral or the other, captured satellites circling their gravitational hosts, while others drift through the group on more independent paths. The Triangulum galaxy, also called M33, represents another notable presence in the region between and near the two great spirals, smaller than either, but still containing tens of billions of stars. Triangulum may participate in the eventual merger as well, though its role remains less certain than the direct collision between the Milky Way and Andromeda that will definitely occur. The galaxy appears in Earth's night sky as another faint smudge, even more challenging to spot than Andromeda, visible under excellent conditions as a dim patch of light in its namesake constellation. The local group contains these three larger spirals, plus the many dozens of smaller dwarfs, all bound together by gravity. Dark matter fills the space between galaxies invisibly, contributing gravitational attraction without producing any light that might reveal its presence directly to observation. The dark matter halos surrounding both the Milky Way and Andromeda extend far beyond their visible edges, reaching outward into the intergalactic space, and likely already overlapping with each other, despite the separation that remains between the visible portions. This invisible component carries most of the mass in the system, outweighing the visible stars and gas by roughly 5-to-1, and provides much of the gravitational force drawing the galaxies together. The merger involves dark matter as much as visible matter, unseen masses falling toward each other across the cosmic void. The current distance represents a temporary state in an ongoing process that has been narrowing the gap since the beginning of the universe, and will continue until the galaxies finally merge billions of years from now. The distance was greater in the past, with the galaxies more widely separated when both were young, and will be smaller in the future as the approach continues across coming billions of years. Nothing about this distance is permanent or stable. Only the momentary snapshot of a dynamic process captured at this particular instant in cosmic time. The void is shrinking, slowly but inevitably, as gravity draws everything together. The journey across this gulf, even at the tremendous speed of approach, takes so long that stars are born and die while the gap continues closing. Generations of stellar life cycling through while the distance remains vast. A star like our Sun, living roughly 10 billion years from birth to death, could complete its entire existence in less time than the approach requires from the current moment to the collision. The timescales of galactic dynamics exceed even the lifespans of long-lived stars, operating on a level above the stellar processes that we often consider slow by human standards. Stars seem patient, but galaxies are more patient still. The void between galaxies holds a kind of significance, precisely because it represents the scale on which gravitational systems exist in the universe, the distances that matter for understanding cosmic structure. Within galaxies, stars are separated by light years, vast distances by human standards, but small compared to the intergalactic gulfs. Between galaxies, millions of light years of emptiness establish the spacing of the cosmic web, the pattern of filaments and voids that organizes matter on the largest scales. The 2.5 million light-years between the Milky Way and Andromeda represents a typical spacing for neighboring galaxies in dense regions of this cosmic structure. Crossing the void at light speed would still require 2.5 million years, making communication between galaxies effectively impossible across such distances, even for hypothetical civilizations capable of sending signals at the ultimate speed limit. A message sent from the Milky Way to Andromeda would take 2.5 million years to arrive, with any reply requiring another 2.5 million years for the return journey. The isolation between galaxies is profound, the distances creating separation that matters, even for phenomena traveling at the maximum possible speed. The void is a barrier in time, as much as in space. The approach across this gulf happens in darkness, the space between galaxies containing almost no light, except for the distant glow of the galaxies themselves and the faint background radiation left over from the cosmic beginning. If somehow observers could exist in the intergalactic medium, they would see only distant points and smudges of light. The galaxies of the local group and beyond, scattered across the sky, without the concentrated glow of a galactic disk surrounding them. The darkness of intergalactic space is nearly absolute, interrupted only by the light reaching it from distant sources that appear small and faint from such vantage points. Despite the immense scale of this gulf, the approach is closing it steadily, bringing together two structures that will eventually merge into a single galactic system, combining the stars and gas and dark matter of both. The void is temporary, a separation that will end in collision and merger across the timescales required for such vast distances to be crossed at such vast speeds. Everything about the relationship between these two galaxies points toward unity, toward combination, toward a future where the gap no longer exists and the two have become one. The void between exists now, but will not exist forever. The question that might arise when contemplating a collision between two galaxies, each containing hundreds of billions of stars, is whether such an event would be catastrophic and violent, as the word collision might suggest. The collision between the Milky Way and Andromeda, despite the dramatic language of merging and colliding, will be surprisingly gentle for the individual stars caught up in the process over billions of years. Galaxies are mostly empty space, with stars separated by such vast distances that close encounters between individual stars during the merger will be extraordinarily rare and unlikely. The typical spacing between stars in our region of the Milky Way measures roughly 4 to 5 light years, a distance so enormous that even during a galactic collision, stars pass each other without significant interaction. Two swarms of stars can interpenetrate and emerge on the other side, with almost no stars having come close enough to affect each other gravitationally. The emptiness between stars creates a fundamental difference between collisions at human scales and collisions at cosmic scales, where the word means something quite different from what we typically imagine. When two solid objects collide in everyday experience, their surfaces touch, their atoms interact, and energy transfers through direct physical contact between the materials involved. Galaxies have no surfaces in this sense, no solid boundaries that could touch another galaxy's boundary, only collections of stars separated by light years of nearly empty space. The merger proceeds through gravitational interaction rather than physical contact. Stars reshuffled by shifting gravitational fields rather than impacted by other objects. To understand the emptiness within galaxies, consider that if our Sun were reduced to the size of a grain of sand, the nearest other star would be placed roughly 4 miles away on that same scale. The 2 grains of sand representing neighboring stars would have miles of empty space between them, making collision between them almost impossible, even if both moved through the same region. Scale this up to billions of stars in each galaxy, and the collision becomes 2 sparse swarms passing through each other, with individual members rarely coming close enough to interact significantly. The galaxies merge, but the stars within them do not collide in any meaningful sense. Simulations of galaxy mergers demonstrate this gentleness clearly, showing stars passing each other during the interpenetration of 2 galactic structures, without significant close encounters between individual objects. Computer models track the motion of billions of simulated particles, representing stars and dark matter, calculating gravitational interactions across millions of years of simulated cosmic time. These simulations show the galaxies distorting, stretching, forming tidal tails of stars flung outward by gravitational forces. But they do not show significant numbers of stellar collisions. The merger is gravitational, not physical, reshaping the distribution of stars without destroying them. What does interact during a galaxy merger is the gas and dust that fills the space between stars within each galactic disk. Material far more diffuse than stars, but distributed more continuously through the galactic volume. Gas clouds can collide with each other during the merger process, their sparse material compressing and heating as the clouds encounter each other at significant velocities. This compression triggers star formation, with dense regions in the compressed gas collapsing gravitationally to form new stars at rates much higher than either galaxy experienced before the merger began. Galaxy collisions actually create stars rather than destroying them, at least during the early phases of the merger process. The gravitational effects of the merger, while not causing stellar collisions, do significantly affect the orbits of stars throughout both galaxies involved in the process. Stars that previously followed stable orbits around their galactic centers find those orbits disrupted by the changing gravitational field as the 2 galaxies interact and interpenetrate. Some stars are flung outward into intergalactic space, forming long tidal tails of material stripped from the main galactic bodies by gravitational forces during close passages. Other stars fall inward toward the combined center of mass, contributing to the dense central regions of the eventual merged system. The reshuffling of stellar orbits occurs over millions and billions of years, far too slowly to observe as motion during a human lifetime, but clearly visible in the distorted shapes of merging galaxies observed throughout the universe. Astronomers have photographed many examples of galaxy mergers in progress, cosmic car crashes happening in slow motion across millions of light years of distance and millions of years of time. These images show the stretched shapes and tidal tails predicted by simulations, confirming that the models accurately represent the the physical processes occurring during such events. The gentleness of the stellar dynamics contrasts with the dramatic visual appearance of these distorted, interacting systems. The Milky Way has likely absorbed smaller galaxies in the past, with evidence suggesting that our galaxy grew partly through mergers with dwarf galaxies, captured and consumed over billions of years of cosmic history. These past mergers left traces in the form of stellar streams, elongated groups of stars on similar orbits that represent the remnants of disrupted dwarf galaxies gradually being absorbed into the larger structure. The Milky Way will survive its merger with Andromeda in a similar sense, though transformed, with both original galaxies contributing their stars to a new combined structure rather than one destroying the other. Merger is growth, not destruction, at the galactic scale. The chance of our own sun being significantly affected by a close stellar encounter during the merger remains essentially zero, far too low to consider a meaningful possibility, given the statistics involved. Even across billions of years and billions of stars passing through the same regions of space, the probability of any two stars coming close enough to disrupt planetary orbits is negligible. The Sun and its planets, if they still exist by that epoch, will continue orbiting whatever gravitational center the merged galaxy presents, their paths altered by the overall restructuring, but not by close encounters with specific stars. The merger changes the map, but individual locations on the map remain relatively undisturbed. The transformation of galactic structure during the merger proceeds through gravitational dynamics rather than violent collision, with the beautiful spiral arms of both galaxies gradually dissolving as the organized rotation that maintains them becomes disrupted by the interaction. Spiral arms depend on orderly rotation, with stars following roughly circular paths around the galactic center, and the gravitational chaos of the merger destroys this order over time. The merged galaxy will likely settle into an elliptical shape rather than maintaining spiral structure, with stars moving on more random orbits through a roughly spherical or oval distribution. The transformation is fundamental, changing the entire character of the stellar system. This gentle violence, if such a paradox makes sense, defines the nature of cosmic processes that sound dramatic but unfold too slowly and too diffusely to match human intuitions about collision and impact. The universe operates through patient gravitational interaction, through slow accumulation and redistribution of matter across timescales that dwarf human comprehension and human experience. The merger will be magnificent when viewed across billions of years, transforming the night sky and creating a new galactic structure from the combination of two older ones. Yet, moment to moment, year to year, the process will be imperceptible, stars continuing their paths without disruption. The safety of individual stellar systems during the merger means that any hypothetical life existing in either galaxy at the time of collision would not necessarily face catastrophe from the merger itself, though other factors, like stellar evolution, would continue operating independently. A civilization existing around a star in the Milky Way or Andromeda would experience a changing night sky across millions of years, watching the other galaxy grow larger and eventually surrounding them, but would not face collision or impact from individual approaching stars. The danger, such as it exists, comes from the changing galactic environment rather than from direct collision with approaching objects. The merger represents transformation rather than destruction. Two galaxies combining their hundreds of billions of stars into a single structure containing the combined population of both, larger and more massive than either original. No stars are lost in this process, though some are redistributed to different regions, and some are ejected entirely into intergalactic space. The total count increases rather than decreases, with bursts of star formation during the merger adding new stars to the population. The violence is creative, building something new from the combination of older components. Understanding the gentleness of the merger allows us to envision the changing night sky without fear, appreciating the cosmic spectacle for its beauty and transformation, rather than worrying about catastrophic destruction that will not actually occur. The sky will change dramatically, filling with new light and new patterns as Andromeda approaches and eventually merges with our galactic home across billions of years of patient transformation. The changes will be visible to any observers who exist to watch them. A slow-motion show spanning epochs far beyond any individual lifetime, with the understanding that the merger will be gentle rather than catastrophic. We can begin to envision what the night sky will actually look like as the process unfolds. Starting with the first visible changes, still roughly 1 billion years in the future. The night sky, 1 billion years from now, will show the first clearly visible changes in Andromeda's appearance, the galaxy having traveled roughly a quarter of the remaining distance toward our position within the Milky Way. The soft smudge visible tonight will have grown noticeably larger, perhaps twice its current apparent size, though still appearing as a faint glow to unaided eyes on dark nights. The change will have happened so slowly that no individual observer could have witnessed the transformation. But comparison with ancient records would reveal unmistakable growth in the apparent diameter of our approaching neighbor. The merger is still 3 to 4 billion years distant at this point, but the approach has progressed far enough to produce visible consequences. Earth itself will be a very different place by this epoch, if it exists at all, in a form we would recognize from our current perspective on planetary evolution. Our sun will have aged by 1 billion years, burning slightly brighter and hotter as it slowly exhausts its hydrogen fuel and adjusts its internal structure in response. This increased brightness will have significantly warmed Earth, potentially rendering the surface inhospitable to life as we know it, though the planet itself will continue orbiting its aging star. The observers we imagine looking at this changed sky may need to exist elsewhere, on worlds around younger stars where conditions remain favorable. The constellation patterns familiar to any human who has ever looked up at the night sky will have dissolved entirely over the course of 1 billion years. Stars having moved significantly enough through proper motion to destroy all the shapes that ancient and modern observers named and memorized. The stars that form Orion, the Big Dipper, and every other recognizable pattern will have shifted to new positions, their apparent proximity in our current sky revealed as temporary coincidence when viewed across longer timescales. The sky will contain just as many stars, but arranged in different configurations that no human has ever seen or ever will see directly. Against this unfamiliar stellar background, Andromeda will stand as a more prominent feature, its growth visible through careful observation, even if the change happened too slowly for any single lifetime to notice. The galaxy will still appear as a fuzzy patch rather than a resolved structure to naked eyes, but larger and perhaps slightly brighter than the smudge we see tonight. Telescopes of that era, whatever form they might take, would reveal the spiral structure in greater detail. The galaxy's arms more easily distinguished, its overall shape more apparent from the reduced distance. The approach continues, the gap narrows, and the visual consequences begin to accumulate. 1 billion years represents a span exceeding the entire history of complex life on Earth. From the Cambrian explosion to the present day, multiplied several times over to reach such immense temporal extent. Life evolved from single-celled organisms to the current diversity of species in less time than will pass between now and the epoch we are imagining, illustrating the vast timescales involved in cosmic processes. The universe operates patiently, changes unfolding across periods that make evolutionary time seem brief, galaxies approaching each other while entire biospheres rise and fall on planetary surfaces below. The night sky transforms, but slowly, always slowly. The distance remaining at this point, roughly 1.5 to 2 million light-years, still represents an incomprehensible gulf by human standards, even though significant progress has been made across the preceding billion years. Light will still take millions of years to cross between the galaxies. Communication remaining impossible, even in principle, across such distances, no matter what technologies might have developed in the intervening epochs. The isolation between galaxies persists, even as they approach each other, the gulf remaining vast, even as it narrows steadily through gravitational attraction. The Milky Way itself will have evolved over this billion-year span, its spiral arms rotating through several complete turns around the Galactic Center during the interval. Stars will have formed and died. Supernovae will have scattered elements through the interstellar medium, and the overall structure of our galaxy will have changed in subtle ways through internal dynamics and the ongoing consumption of dwarf satellite galaxies. The Milky Way absorbs smaller galaxies regularly on cosmic timescales, growing through merger even before the major collision with Andromeda begins in earnest. The visual appearance of the Milky Way from within will remain broadly similar, the band of light crossing the night sky still visible from any dark location, on whatever worlds might host observers in that distant epoch. The position of those observers within the galaxy might be different, the Sun having migrated somewhat through its orbit. But the general experience of being inside a spiral galaxy and seeing its disk as a band of light would persist. The sky would show both the familiar galactic band and the increasingly prominent glow of the approaching Andromeda spiral. Two great structures drawing together across the cosmic void. The local neighborhood of stars around wherever the Sun exists at that time will have changed significantly, with nearby stars having moved to new positions and new stars having entered the neighborhood while old neighbors drifted away. The Sun's nearest stellar neighbors in a billion years will be entirely different from Alpha Centauri and the other stars we currently consider our closest cosmic companions in the galactic environment. Stellar neighborhoods are temporary, proximity in space meaningful only across limited time spans, before proper motion reshuffles all the familiar arrangements. Only the distant structures retain their recognizable forms across such immense periods. The approach velocity may have increased slightly by this point, gravitational attraction intensifying as the distance decreases, and the inverse square relationship that governs gravitational force becomes more favorable. This acceleration is subtle, adding perhaps a few kilometers per second to the approach velocity over 1 billion years. But the cumulative effect matters across such long periods. The galaxies fall toward each other with increasing speed, though the motion remains imperceptible to any individual observer across any reasonable observation period. Patient instruments might detect the change over centuries, but no living being would perceive it directly. The sky in 1 billion years represents a waypoint on the journey rather than a destination. The merger still distant enough that daily life, wherever and whatever form it might take, would proceed without noticeable impact from the approaching galaxy. An observer in that epoch would see a larger smudge in the sky and might know intellectually that a collision lay billions of years in the future. But the knowledge would carry no urgency and demand no response. The universe presents its transformations on timescales that allow observation without requiring action. Changes that happen regardless of whether anyone watches or cares. The sun in that era, our sun aged by 1 billion years, will be approaching a critical phase of its evolution, though not yet reaching the dramatic transformations that lie further ahead in its life cycle. The increased luminosity that has gradually rendered Earth less hospitable will continue increasing, the sun slowly brightening as it ages and burns through its hydrogen reserves. The relationship between solar evolution and galactic approach creates a peculiar synchronization, both processes reaching their most dramatic phases at roughly similar times in the cosmic future. The sun will die, and the galaxies will merge at roughly the same epoch, coincidence or not. This epoch, 1 billion years hence, represents the beginning of visible change. The first clear signs that the approach is producing consequences that would be apparent to careful observers comparing the present sky to records from the distant past. The merger remains far off, but its inevitability has begun to manifest in the growing apparent size of our approaching neighbor, the gap narrowing visibly across the immense span of 1 billion years. The transformation has begun, though most of it still lies ahead across the next several billion years of cosmic time. As another 2 billion years pass beyond this point, the changes accelerate dramatically, Andromeda growing to dominate the night sky as the merger approaches its most spectacular phases. 3 billion years from the present, the night sky will show Andromeda as a dominant feature rather than a subtle smudge. The galaxy, having closed much of the remaining distance and grown enormously in apparent size as seen from our solar system's position. The spiral structure will be clearly visible to unaided eyes on dark nights. The arms of the galaxy, tracing graceful curves across a significant portion of the sky, far larger than any constellation visible tonight. This will not be a faint object requiring dark-adapted eyes and careful searching, but a major feature of the night that anyone looking up would immediately notice and recognize as something extraordinary. The apparent size of Andromeda at this epoch may span several degrees across the sky, many times the width of the full moon, making it one of the most prominent objects in the heavens, apart from the sun and moon themselves. The bright central bulge will glow distinctly, surrounded by the darker regions of the spiral arms, where dust lanes wind between the brighter stellar populations. The entire structure hanging in space with a clarity impossible at today's distance. The view will be magnificent by any measure, a galaxy filling the sky in a way that no human has ever witnessed from Earth or any other vantage point in the solar system. The night will hold a new kind of beauty, unfamiliar and awesome. Our sun will be nearing the end of its main sequence life by this point, having burned hydrogen in its core for roughly 8 billion years since its formation, and approaching the transition to red giant stage that marks the final phases of its stellar evolution. The sun will have grown significantly more luminous over these 3 billion years, likely heating Earth far beyond the temperatures compatible with liquid water and life as we know it. The planet may still orbit, but the conditions on its surface will be hostile, transformed by the increasing energy output of an aging star approaching a dramatic transformation. Any observers who witness this sky will necessarily exist on other worlds, around other stars, in locations where conditions remain favorable for whatever forms of complexity and awareness might have developed or spread across the galaxy over 3 billion years. These observers might be descendants of terrestrial life that spread to other star systems, or they might be entirely independent developments with no connection to Earth's evolutionary history at all. Whoever or whatever they are, they will see a sky dominated by Andromeda in a way that makes our current view seem pale and distant by comparison. The two galaxies at this point will be separated by something like 500,000 to 1 million light years, having closed the vast majority of the original gap through patient gravitational approach across the preceding billions of years. The remaining distance still exceeds comprehension by human standards, but the change from 2.5 million light years represents dramatic progress in the slow merger process. The final approach accelerates as gravity intensifies, the remaining distance closing faster than the earlier portions of the journey, despite the velocity remaining too slow to perceive across short timescales. The spiral arms of Andromeda will show individual star-forming regions to sufficiently powerful telescopes, bright knots of young stars and glowing gas clouds that dot the arms of all spiral galaxies as they continuously produce new stellar generations. The structure will appear magnificent in its detail. A spiral galaxy, seen as the ancient humans who first noticed that faint smudge, could never have imagined seeing it. The transformation will be complete in terms of Andromeda's visual appearance, from subtle smudge to sky-dominating spiral across 3 billion years of patient approach. The dark matter halos of both galaxies will almost certainly have begun interacting significantly by this point, their invisible masses interpenetrating across the remaining gap and affecting the gravitational dynamics of both structures. This interaction may already be producing subtle distortions in the outer regions of both galaxies, the first hints of the tidal forces that will dramatically reshape both structures during the close passages still to come. The merger has begun in a gravitational sense, even while the visible structures remain clearly separated in space. The local group will have evolved significantly over these 3 billion years, with the smaller dwarf galaxies continuing to orbit and occasionally merge with the larger spirals that dominate the group's mass. The Triangulum galaxy may have grown closer to one or both of the major spirals, potentially participating in the eventual merger or maintaining its own separate existence, depending on the precise orbital dynamics. The neighborhood of galaxies remains gravitationally bound and continues its internal evolution even as the major merger between the two largest members approaches. Looking back toward the position of Earth, if the Sun and its planets still existed in some form, the view would show Andromeda behind rather than ahead. the relative position having shifted as the galaxy passes various angles relative to our solar system's orbital position within the Milky Way. The changing view depends on position, with different locations within either galaxy seeing different perspectives on the approach and eventual merger. The experience will not be uniform, but will vary across the hundreds of billions of star systems contained within both galaxies. The night sky from Earth's position, even if Earth itself is no longer habitable or no longer exists in recognizable form, will show both the familiar band of the Milky Way from within and the enormous spiral of Andromeda from without, two great galactic structures sharing the same sky as they prepare for their final approach. The visual contrast between interior view and exterior view will be striking, the Milky Way appearing as a band, while Andromeda appears as a disk seen at an angle. Two different perspectives on similar structures from different positions relative to their boundaries. The remaining billion-plus years until first close passage will continue transforming the sky, with Andromeda growing larger still and the first tidal distortions potentially becoming visible as the gravitational interaction intensifies. The pace of visible change accelerates as the merger approaches, with more dramatic transformations occurring in the final phases than in the long, slow approach that preceded them. The patient journey across billions of years gives way to a more dynamic phase as the galaxies finally begin their close encounter. The epoch 3 billion years hence represents the last phase of Andromeda as a clearly separate object in the sky, a distinct galaxy approaching but not yet merged with our own Milky Way structure. Within another billion years, the first close passage will occur, and the two galaxies will begin interpenetrating, their stars mixing in the gravitational dance that eventually produces a single combined structure. The sky we envision at 3 billion years shows the last view of two distinct great spirals sharing a cosmic neighborhood before they begin becoming one. The transformation already evident by this point will intensify dramatically as the final billion years pass and the galaxies make their first close approach to each other. Approximately 4 billion years from now, the Milky Way and Andromeda will make their first close passage. The cores of the two galaxies sweeping past each other at a distance of perhaps 100,000 light-years, while their outer regions interpenetrate in a gravitational embrace. This first encounter marks the beginning of the merger proper, the transition from approach to interaction, the moment when two separate galaxies begin becoming a single combined structure through gravitational dynamics unfolding across cosmic time. The night sky during this epoch will show both galaxies simultaneously, their stars mixing overhead in patterns never before visible from any location within either original structure. The view from what was once the position of our solar system will be extraordinary. Assuming any remnant of our stellar neighborhood still exists by this point, in a recognizable location within the transforming galactic structure, the sky will contain two distinct galactic cores, two bright concentrations of billions of stars, each occupying different regions of the sky, while their combined stellar populations form a single glowing expanse across the heavens. The familiar band of the Milky Way will have been disrupted, stretched and distorted by the gravitational forces acting on our galaxy during the encounter, its organized spiral structure beginning to dissolve. Our sun will have become a red giant by this epoch, having exhausted the hydrogen fuel in its core, and expanded to enormous size as it transitions through the final stages of its stellar evolution. The expansion will have engulfed Mercury, Venus, and possibly Earth, depending on the precise dynamics of the expansion and the orbital evolution of the inner planets during the process. Whatever remains of Earth, whether engulfed, scorched, or ejected to a wider orbit, will no longer be the familiar world that served as the starting point for this journey through cosmic time. The first passage does not complete the merger, but initiates a process that will continue for approximately 2 billion more years as the galaxies separate, fall back together, and repeat the close encounter multiple times before finally settling into a single combined structure. The gravitational dynamics of the encounter dissipate orbital energy, ensuring that each subsequent passage brings the galaxies closer together and prolongs their interaction. The merger proceeds through this series of encounters, rather than happening in a single dramatic moment. A dance spanning billions of years. Tidal forces during the first passage will pull streams of stars from both galaxies, creating long tails of material extending millions of light years into intergalactic space. These tidal tails represent stars gravitationally stripped from the outer regions of each galaxy, flung outward by the differential gravitational forces acting on near and far sides of each structure. The tails will glow faintly with the combined light of billions of displaced stars, graceful arcs tracing the history of the gravitational interaction that produced them. Some of these stars will eventually return to the combined galaxy, while others may drift into intergalactic space permanently. The night sky during first passage will show these tidal features as faint extensions of light stretching away from the brighter central regions of both galaxies, luminous ribbons marking the progress of the merger across the heavens. The visual appearance will differ dramatically from any sky humans have ever seen. Two galaxies interpenetrating with stars from both systems visible overhead, their structures distorting in response to each other's gravity. The organized beauty of spiral arms will give way to more chaotic arrangements as the gravitational disruption progresses. Star formation will increase dramatically during the first passage as gas clouds from both galaxies collide and compress, triggering the gravitational collapse that produces new stars at rates far exceeding the normal pace in either original galaxy. These bursts of star formation will illuminate the colliding gas with the blue-white light of hot young stars, creating bright regions scattered through the merging structures where stellar birth occurs at elevated rates. The merger destroys the organized structure of both galaxies, but creates new stars in the process, transformation rather than simple destruction. The central supermassive black holes of both galaxies will remain in their respective cores during the first passage, separated by the same roughly 100,000 light years as the galactic centers themselves during this initial encounter. These black holes will eventually spiral toward each other and merge. But that final gravitational encounter lies in the future, requiring additional passages and the continued dissipation of orbital energy before the cores approach closely enough for the black holes to interact directly. The relative velocity of the two galaxies during first passage may have increased somewhat from the current approach velocity of 110 kilometers per second, gravitational acceleration having added energy to the system as the galaxies fell toward each other across the preceding billions of years. The encounter will happen at considerable speed by human standards, though still slowly enough that the interpenetration takes millions of years rather than occurring as a rapid event. The passage unfolds in cosmic slow motion, imperceptible, moment to moment, but dramatic across longer timescales. From a position within the merging galaxies, the sky will contain stars from both original systems, the stellar populations mixing as the structures interpenetrate during the passage. The density of visible stars may increase significantly as material from both galaxies occupies the same general region of space, though the vast distances between individual stars mean this mixing produces no collisions. The sky simply becomes richer with light, more stars visible than ever before, as two galactic populations share the same cosmic neighborhood. The chaos of the first passage will gradually give way to a temporary separation as the galaxies move through each other and begin drifting apart before gravity pulls them back for subsequent encounters. The tidal tails will remain as visible evidence of the interaction, but the main bodies of both galaxies will separate and reach maximum distance before falling back toward each other again. This oscillation between approach and separation characterizes the middle phase of the merger, the gravitational dance that eventually exhausts orbital energy and forces the final combination. The epoch of first passage represents the most visually dramatic moment of the merger process, when both galaxies are simultaneously visible as they interpenetrate and distort each other through gravitational forces operating across cosmic distances. Earlier epochs showed Andromeda approaching as a separate object. Later epochs will show a single combined structure settling into its final form. This moment of first passage captures the transition between those states, two becoming one, through a process that spans the following 2 billion years. The first close encounter will end with the galaxies separating, moving apart temporarily, before gravity inevitably draws them back together for subsequent passages that bring them ever closer to final merger. Following the first close passage, the two galaxies will separate and move apart, their momentum carrying them through and beyond each other, despite the gravitational attraction that will inevitably reverse their motion and draw them back together. This separation represents a temporary state, a pause in the merger process, during which the galaxies reach maximum distance before falling back toward each other for another close encounter. The oscillation between approach and separation will continue for approximately 1 to 2 billion years, with each subsequent passage bringing the structures closer together and more thoroughly mixed. The tidal tails created during the first passage will persist throughout this period, elongated streams of stars connecting the separating galaxies and tracing the gravitational history of their interaction across millions of light years. These luminous threads will glow faintly with the combined light of the billions of stars they contain. Material stripped from both galaxies, but still gravitationally connected to the combined system. The tails represent stars in transition, temporarily displaced but destined to eventually return to the merged galaxy, or drift into permanent intergalactic exile. The night sky during the separation phase will show the two galactic cores moving apart, their central concentrations of light receding from each other, while the tidal tails maintain their connection across the growing gap. Observers within either structure would see the other galaxy pulling away, its bright center shrinking with distance, while the connecting streams of stars mark the path between them. The visual appearance will change continuously across millions of years, the dynamic nature of the encounter visible through the shifting positions and structures. The gravitational energy dissipated during each passage comes from the orbital motion of the galaxies around their common center of mass, with each close encounter converting kinetic energy into potential energy stored in the tidal tails and the disrupted stellar orbits throughout both structures. This energy loss ensures that subsequent passages occur at lower velocities and bring the galaxies closer together, the system gradually spiraling toward final merger through repeated encounters that drain its orbital energy. The process is self-limiting, each interaction advancing the merger toward its inevitable conclusion. The second close passage will produce additional tidal distortions, further disrupting the already damaged spiral structures of both galaxies and adding new material to the existing tidal tails, or creating new streams of displaced stars. The galaxies become progressively more irregular with each encounter, their original spiral organization dissolving into a more chaotic arrangement of stars on disrupted orbits. The beauty of spiral arms gives way to a different kind of beauty, the graceful chaos of gravitational interaction reshaping cosmic structure. Between passages, the galaxies exist in a state of mutual gravitational capture, bound together even while temporarily separated and moving apart from each other at significant velocities. The orbital paths become increasingly complex as the irregular mass distributions of the distorted galaxies produce gravitational effects that differ from the simple point mass approximations that describe more distant interactions. The dynamics require detailed computer simulation to predict accurately, the merger proceeding through paths that depend on the precise initial conditions and mass distributions of both interacting systems. Star formation continues at elevated rates throughout this period, with gas clouds colliding and compressing whenever the galaxies pass close enough for their interstellar media to interact significantly. The bursts of star formation that began during first passage continue during subsequent encounters, producing generations of new stars in regions where the gas clouds from both galaxies meet and compress. This elevated star formation gradually depletes the gas reserves of both galaxies, using up the raw material that produces stars and setting the stage for the eventual quiet of the merged galaxy. The central black holes of both galaxies remain separated throughout the early phases of the merger, their cores orbiting each other at distances that initially measure hundreds of thousands of light years, but gradually shrink with each passage. The black holes feel the gravitational effects of the merger through the changing distribution of stellar mass surrounding them, their orbits influenced by the overall dynamics, even while direct interaction between them remains far in the future. The final merger of the black holes will represent the culmination of the entire process, occurring millions of years after the galactic cores first approach closely enough for the black holes to interact. The sky, during the phase of repeated passages, will show continuous transformation, with the visual appearance of the surrounding stellar populations changing noticeably across timescales of millions of years as stars shift to new orbits and tidal features evolve. No observer alive at any moment could witness the change directly, but records maintained across sufficient time would reveal the dramatic evolution of the night sky throughout this dynamic phase. The universe operates slowly by human standards, but the changes during this phase proceed rapidly by cosmic standards. Some stars, ejected during the tidal interactions, will achieve velocities sufficient to escape the combined gravitational pull of the merging system entirely. becoming intergalactic wanderers, drifting alone through the void between galaxy groups. These ejected stars may carry planetary systems with them, worlds torn from their galactic neighborhood and cast into the darkness between structures on timescales measured in billions of years. The ejection represents a small minority of the total stellar population, but the absolute numbers remain enormous when dealing with galaxies containing hundreds of billions of stars each. The repeated passages gradually blend the stellar populations of both original galaxies, mixing stars from Andromeda and the Milky Way into a single combined population distributed throughout the merging structure. The distinction between stars that originally belonged to one galaxy or the other becomes increasingly meaningless as the merger progresses and the two populations become thoroughly intermixed. The final merged galaxy will contain stars from both ancestors, their origins detectable through detailed analysis, but no longer representing separate populations in any spatial sense. The period of repeated passages represents the active phase of the merger, when the most dramatic visual changes occur, and the gravitational dynamics reshape both structures most significantly. The chaos of this period will eventually give way to the settling calm of the final merged galaxy. But for roughly 2 billion years, the system exists in a state of dynamic transformation. The night sky evolves continuously, showing different configurations at different epochs, as the merger proceeds through its complex gravitational choreography. The conclusion of the repeated passages comes when the orbital energy has been sufficiently dissipated that the two galactic cores can no longer separate, falling together into a final merger that combines both structures into a single galaxy. The final merger of the two galactic cores occurs approximately 6 to 7 billion years from the present, marking the conclusion of a process that began with the first gravitational attraction between the two structures billions of years earlier. The cores approach each other for the last time. No longer able to separate, their combined gravitational pull drawing them together into a single, dense, central concentration of stars and the supermassive black holes they contain. This moment represents the completion of the merger in structural terms, two galaxies becoming one through the patient work of gravity across cosmic time. The supermassive black holes at the centers of both original galaxies spiral toward each other during this final phase, their orbital separation shrinking from thousands of light years to hundreds, and then to the final astronomical units before merger. The approach proceeds through gravitational interaction with surrounding stars, which carry away orbital energy and allow the black holes to sink closer together over millions of years. The process is called dynamical friction, the gravitational drag created by interactions between the black holes and the dense stellar populations surrounding them in the combined galactic core. The actual merger of the two black holes occurs rapidly once they approach closely enough for gravitational radiation to become significant. The emission of gravitational waves draining the remaining orbital energy and bringing the two objects together in a final spiral lasting perhaps only minutes or hours. This final coalescence releases energy equivalent to millions of solar masses, converted entirely into gravitational waves, ripples in the fabric of space-time that propagate outward at the speed of light, carrying news of the merger to the wider universe. The gravitational waves from such an event would be detectable by sufficiently sensitive instruments throughout the observable universe. The combined black hole that results from this merger will contain roughly 100 million solar masses, or more, representing the sum of both original black holes plus any additional material consumed during the active merger phase. This enormous concentration of mass will anchor the center of the new galaxy, providing the gravitational core around which all the combined stellar population will orbit. The black hole will remain invisible directly, its presence detectable only through its gravitational effects on surrounding matter and the occasional consumption of gas or stars that stray too close to its event horizon. The merged galaxy settles into its final form over hundreds of millions of years, following the core merger, with stars on chaotic orbits gradually finding stable paths through the new gravitational potential created by the combined mass distribution. The spiral structure of both original galaxies has been completely destroyed by this point, replaced by a more irregular arrangement that will eventually settle into an elliptical shape as the system relaxes. Elliptical galaxies have a roughly spherical or oval distribution of stars, rather than the flat disks of spirals, reflecting the randomized orbits that result from major merger events. The night sky during the final merger phase will show a single concentrated galactic structure, rather than the two separate cores visible during earlier epochs. The combined light of both original central bulges merged into a single bright region, surrounded by the combined stellar populations. The tidal tails will have largely dissipated by this point, their material either returned to the main galaxy or ejected permanently into intergalactic space. The visual appearance begins transitioning toward the calmer configuration of the settled merged galaxy. Star formation rates will decline following the final merger, as the gas that fueled elevated star formation during the active merger phase has been largely consumed or expelled from the system by the energetic processes accompanying the interaction. Mergers often trigger bursts of activity that use up available gas, leaving the resulting galaxy with less raw material for future star formation than either original galaxy possessed. The merged galaxy will be a quieter place than either ancestor, its star-forming days largely behind it as it settles into cosmic middle age. The combined stellar population of the merged galaxy will number roughly 1.5 trillion stars. The sum of both original galaxies' stellar inventories, plus the new stars formed during the merger, minus those ejected into intergalactic space. This population will include stars of all ages, from ancient objects formed in the early universe, to young stars formed during the merger bursts, to whatever stellar birth continues at reduced rates following the final combination. The diversity of stellar ages reflects the merged origin, with stars from both original galaxies contributing to the combined population. The merged galaxy has been given the nickname Milkdromeda, or Milkdromeda, by astronomers who enjoy speculating about future cosmic events. A playful combination of the names of the two ancestral galaxies. The name acknowledges the merged nature of the final structure, descended from both the Milky Way and Andromeda through a process of gravitational combination spanning billions of years. Whether any observers will exist in that distant future to call the galaxy by any name remains unknown, but the structure itself will exist regardless of who might be there to observe and name it. The transition from active merger to settled galaxy proceeds gradually, with no sharp boundary marking the moment when the merger ends and normal galactic existence begins. The system simply becomes calmer over time. The chaotic motions of the merger phase settling into more orderly orbits, the visual appearance becoming more stable, the rate of structural change declining toward the slow pace characteristic of isolated galaxies. The merged galaxy exists as a single structure, its dual ancestry evident in detailed analysis, but not obvious from casual observation. The local group as it exists today will have been significantly transformed by this epoch, with the Milky Way and Andromeda combined into Milkdromeda, and the smaller member galaxies either absorbed into the merger or continuing to orbit the combined structure as satellites. The Triangulum galaxy may have been absorbed into the merger or may continue as a separate structure, depending on orbital dynamics too complex to predict with certainty from current observations. The cosmic neighborhood will look very different from its present configuration. The completion of the merger represents an ending and a beginning, the conclusion of two separate galactic histories, and the start of a new combined history that will continue for trillions of years into the cosmic future. The night sky, as seen from within the merged galaxy, will differ fundamentally from any sky visible from Earth today. The organized band of the Milky Way, replaced by a more uniform distribution of stars, scattered across all directions of view. Elliptical galaxies lack the disk structure that produces the familiar band of light visible from within spiral galaxies, their stars orbiting in all directions rather than confined to a relatively thin plane. An observer within Milkdromeda will see stars in every direction, without the concentration toward a galactic plane that characterizes our current view from inside the Milky Way's disk. The brightness and density of visible stars will depend strongly on position within the merged galaxy, with locations near the center surrounded by far more stars than positions in the outer regions of the roughly spherical or oval structure. An observer near the Galactic Center would see a night sky blazing with stars, their combined light perhaps bright enough to affect the darkness of night on any planets orbiting in such regions. An observer in the outer regions would see fewer stars, the night sky darker and more similar to views from isolated regions, far from galactic centers. The core of the merged galaxy will contain the combined supermassive black hole, 100 million solar masses or more of concentrated matter, invisible except through its gravitational effects on surrounding stars and material. The black hole will be quiet by this epoch, lacking the active accretion that produced quasar-like behavior in the early universe, simply sitting at the gravitational center while stars orbit around it at various distances. Occasionally, material may fall toward the black hole and produce brief flares of radiation, but such events will be rare in the settled, merged galaxy. The stellar population of Milkdromeda will include stars spanning a wide range of ages, from ancient objects formed in the first billion years of cosmic history to relatively young stars formed during the merger bursts just a few billion years before the epoch we are imagining. The mix of ages reflects the combined histories of both ancestral galaxies plus the star formation triggered by their interaction, a diverse population brought together through gravitational combination. Red giant stars, white dwarf remnants, and main sequence stars of various sizes will all contribute to the stellar inventory. The Triangulum galaxy, if it survived as a separate structure through the merger epoch, may be visible as a distinct object in the sky of the merged galaxy, a smaller spiral orbiting the larger elliptical structure formed from the combination of its former neighbors. This companion galaxy would provide a visual contrast to the surrounding elliptical structure, a reminder of what spiral galaxies look like when seen from outside. Alternatively, Triangulum may have been absorbed into the merger, its stars added to the combined population of Milkdromeda. The overall appearance of the night sky from within Milkdromeda will be softer and more uniform than the dramatic contrasts visible from inside spiral galaxies, where the galactic plane concentrates starlight into a bright band, while other directions appear relatively dark. The elliptical structure distributes stars more evenly across three-dimensional space, producing a more isotropic view without the striking asymmetry of disk galaxies. The beauty will be different rather than lesser, a gentle glow surrounding the observer rather than a concentrated river of light crossing the heavens. Distant galaxies beyond the local group will remain visible to observers within Milkdromeda, their light reaching the merged galaxy just as it reaches our present position within the Milky Way today. The cosmic web of filaments and voids, the clusters and superclusters of galaxies distributed throughout the observable universe, will continue providing targets for astronomical observation and contemplation. The merger changes the local galactic environment, but does not affect the broader cosmic context within which that environment exists. The expansion of the universe will have continued throughout the billions of years leading to this epoch, carrying distant galaxies further away and redshifting their light toward longer wavelengths. Some galaxies visible today may have receded beyond the cosmic horizon by this point, their light no longer able to reach us due to the acceleration of cosmic expansion driven by dark energy. The observable universe may appear somewhat diminished, fewer galaxies visible than are visible today, the darkness between structures deeper and more absolute. Any observers who exist within Milkdromeda will have no direct experience of the Milky Way or Andromeda as separate entities, those ancestral galaxies existing only in historical records, if such records have been maintained across the billions of years since the merger began. The merged galaxy will be their home, the only galactic structure they have ever known, as familiar to them as the Milky Way is to us. They will look up at a different sky, but with the same curiosity that has characterized observers throughout cosmic history. The merged galaxy will be stable, a single gravitationally bound structure containing roughly 1.5 trillion stars orbiting a common center of mass, dominated by the combined supermassive black hole. The chaotic transformations of the merger epoch will have given way to calm, the system settling into the quiet middle age that characterizes most elliptical galaxies throughout the universe. The future holds further evolution, but the dramatic changes of the merger phase are complete. The position of our sun, or rather the remnant left after our sun's death, lies somewhere within this merged structure, a cooling white dwarf drifting through a galaxy, very different from the one where it originally formed. Our sun will have completed its main sequence life and transformed into a white dwarf long before the merger of the galactic cores occurs, the stellar evolution proceeding on its own timeline, independent of the galactic dynamics unfolding around it. The sun will become a red giant in approximately 5 billion years, expanding enormously and consuming the inner planets before shedding its outer layers and collapsing into a dense, white dwarf remnant, roughly the size of Earth, but containing most of the sun's original mass. This transformation will occur during the early phases of the galactic merger, when Andromeda is approaching but the most dramatic interactions still lie in the future. The white dwarf remnant of our Sun will continue orbiting within whatever galactic structure contains it at any given moment. Its path through space, determined by the gravitational dynamics of the merger and the reshuffling of stellar orbits that accompanies such events. The Sun's position within the Milky Way will shift as the merger proceeds, the organized spiral structure dissolving and stars finding new paths through the changing gravitational potential of the combined system. By the time the merger completes, the Sun's remnant may occupy a very different region than its current position. The probability of the Sun's white dwarf remnant being ejected from the galaxy entirely during the merger remains relatively low, perhaps 10 to 20%, based on simulations of galaxy mergers with similar characteristics. Most stars survive the merger within the combined structure, their orbits altered, but not so dramatically that they achieve escape velocity from the merged system. The Sun's remnant will most likely remain part of Milkdromeda, orbiting the combined Galactic Center for trillions of years into the cosmic future. The cooling of a white dwarf proceeds very slowly, with the remnant gradually radiating away its stored thermal energy over timescales measured in billions and eventually trillions of years. The Sun's white dwarf will still be warm and faintly luminous during the merger completion, glowing with the residual heat from its previous existence as a fusion-burning star. Over the following trillions of years, the remnant will continue cooling, growing dimmer and dimmer until it eventually becomes a cold black dwarf. Though the universe is not yet old enough for any white dwarf to have reached this final state, Earth will not survive the red giant phase of solar evolution in any recognizable form, whether engulfed by the expanding sun or scorched into uninhabitability by the increased luminosity that precedes the expansion. The familiar world that served as the starting point for this journey through cosmic time will be transformed beyond recognition, or perhaps destroyed entirely, its material potentially incorporated into the expanding outer layers of the dying sun. Whatever ultimately happens to Earth, it will not be a place where observers might stand to watch the merger unfold. Any remnants of the solar system that survive the sun's red giant phase will drift through the merged galaxy as a unit. The white dwarf remnant, accompanied by whatever outer planets or distant objects remain gravitationally bound to it. Jupiter, Saturn, Uranus, and Neptune may survive in altered orbits, their atmospheres somewhat affected by the red giant phase, but their basic existence preserved through the transformation. The Kuiper Belt and Oort cloud objects will continue orbiting the remnant sun, an ancient solar system drifting through a very different galaxy than the one where it formed. The merger will shift the sun's remnant to a new orbital path through the combined galaxy, the gravitational reshuffling, placing it in a location and on a trajectory different from its original position within the Milky Way. The remnant might move closer to the Galactic Center or further out into the periphery, depending on the complex gravitational dynamics of the merger and the specific interactions that affect its orbit. The position after the merger will be essentially random from our current perspective, determined by factors too complex to predict. The cooling white dwarf will continue glowing for trillions of years following the merger. Its faint light, a remnant of the stellar fire that once warmed Earth and made life possible on a small rocky world orbiting at a comfortable distance. The light will diminish as the remnant cools, growing fainter across timescales that exceed the current age of the universe by enormous factors. Eventually, the glow will fade entirely, leaving a cold, dense object drifting through the merged galaxy, carrying the compressed matter that once formed a living star. The history contained in that remnant, the story of a star that formed from a collapsing gas cloud and burned for billions of years before transforming through red giant to white dwarf, represents one small thread in the enormous tapestry of stellar evolution occurring throughout the galaxy. Billions of stars will have lived and died during the same epochs, each following its own evolutionary path, each leaving its own remnant to drift through the cosmic future. The Sun's story is unique in its details, but typical in its broad outlines. One star among hundreds of billions in each of the ancestral galaxies. The location of the Sun's remnant within Milkdromeda will be unknowable from our present position in time. Too many variables affecting the outcome across the billions of years between now and the merger completion. Somewhere within that merged galaxy of 1.5 trillion stars, a cooling white dwarf will carry the compressed matter of the star that once warmed Earth, drifting on an orbit determined by the gravitational dynamics of the merger. The connection to our present moment will be physical but untraceable. The continuity real but invisible. The Sun's fate reminds us that stellar evolution proceeds regardless of galactic dynamics. Stars, living and dying, on timescales comparable to, but independent of the timescales on which galaxies merge and transform. The merged galaxy Milkdromeda will settle into cosmic quiet following the completion of the merger, its chaotic transformation giving way to the calm existence that characterizes most elliptical galaxies throughout the observable universe. Star formation will continue at reduced rates, limited by the gas remaining after the merger depleted much of the raw material through the intense star formation bursts that accompanied the active phase. The galaxy will age gradually, its stellar population growing older and redder as massive stars die and are not replaced, the blue light of young stars fading from the overall galactic glow. The cosmic future extends far beyond the completion of the merger, stretching trillions of years into epochs where the universe itself will be very different from its current state. Red dwarf stars, the smallest and longest-lived stellar type, can burn their hydrogen fuel for trillions of years, far exceeding the current age of the universe, and continuing to shine long after larger stars have exhausted their fuel and died. These patient stars will be the last lights in the darkening cosmos, maintaining their gentle glow while the universe ages around them. The expansion of the universe, driven by dark energy, will continue accelerating throughout this cosmic future, carrying distant galaxies away from the local group and eventually from Milkdromeda at velocities exceeding the speed of light. This expansion does not violate relativity because it represents the stretching of space itself rather than motion through space. But the practical effect is that light from these receding galaxies can no longer reach us. The observable universe will shrink for future observers. Fewer galaxies visible as more and more are carried beyond the cosmic horizon by accelerating expansion. The night sky from within Milkdromeda in the far future will show only the local galaxy and whatever companions remain gravitationally bound to it, the distant cosmic web having faded from view, as its light can no longer reach across the expanding gulf of space. The universe will appear smaller and lonelier than it appears today. The billions of galaxies visible to present-day astronomers, reduced to a single island of light, surrounded by apparently empty darkness. The reality of a universe filled with galaxies will become harder to detect, eventually requiring inference rather than direct observation. The gradual fading of the stellar population will continue across trillions of years, with successively smaller stars exhausting their fuel and transitioning to white dwarf remnants, while no new stars form to replace them. The gas needed for star formation will be exhausted or expelled from the galaxy, leaving only the existing stellar population to age without renewal. The galaxy will grow dimmer as the average luminosity of its stars declines. The bright blue giants gone first, then the yellow stars like our Sun, finally leaving only the dim red dwarfs and the cooling remnants of larger stars. The white dwarf remnants scattered throughout the galaxy will cool very slowly, their dense matter retaining heat for timescales exceeding the current age of the universe by enormous factors. These remnants will glow faintly for trillions of years, contributing their diminishing light to the overall galactic luminosity, until eventually even they cool to invisibility. The process proceeds in cosmic slow motion, change imperceptible across any reasonable observation period, but cumulative across the vast stretches of time available. The supermassive black hole at the center of Milkdromeda will remain long after the stars have faded, a gravitational anchor persisting through the darkening of the galaxy around it. Black holes evaporate through a quantum process called Hawking radiation, but the timescale for a supermassive black hole to evaporate exceeds a Google years, a number so large that it dwarfs all the timescales we have discussed tonight by factors beyond comprehension. The black hole will be among the last structures in the universe, persisting through epochs where everything else has faded into cold darkness. The cosmic future holds even longer timescales, epochs where protons themselves may decay and matter dissolves into radiation, where black holes finally evaporate and nothing remains except cooling photons spreading through an ever-expanding void. These timescales exceed human comprehension entirely, stretching to numbers that cannot be meaningfully compared to any reference point within human experience. The universe will continue existing, but in forms so different from its current state that the word universe seems inadequate to describe the continuity. The journey through cosmic time that we have taken tonight, from the faint smudge of Andromeda visible in autumn skies to the quiet darkness of the far cosmic future, spans scales that humble any attempt at full comprehension. We began with a galaxy visible to the naked eye, a trillion stars compressed by distance into a soft glow, and traveled forward through 4 billion years to witness its merger with our own Milky Way. We continued further still, to the settling of the merged galaxy and the gradual fading of stellar light across trillions of years, stretching into the cosmic future. The night sky transforms across these spans, from the familiar constellations of the present through the spectacular displays of the merger epoch to the quiet darkness of the far future, when only the local galaxy remains visible against an apparently empty cosmos. The changes happen slowly, imperceptibly across human timescales, but inevitably across the timescales on which the universe operates. Nothing in the cosmos remains static forever, everything transforming through processes that proceed patiently across billions and trillions of years. The faint smudge visible on clear autumn nights tonight contains within it this entire future. The approaching galaxy that will transform our sky and merge with our home to create something new under stars we will never see. The light reaching our eyes tonight has traveled for 2.5 million years, and the galaxy that sent it continues approaching, crossing the void steadily toward an encounter that lies 4 billion years in our future. The universe operates on its own timescales, and we are fortunate to understand enough to glimpse the cosmic story that unfolds across spans far exceeding human lives and human civilizations. The autumn sky holds Andromeda tonight, as it held it for our ancestors and will hold it for our descendants, a faint glow marking the presence of another island universe drifting through the cosmic darkness. The approach continues, the gap narrows, and the future unfolds in cosmic slow motion toward transformations we can predict but never directly witness. The universe is patient, and the night sky changes slowly, and the merger will come in its own time across the billions of years that stretch ahead through the quiet darkness of cosmic time.